Well, we now know what an integral is. It only took, 6 lectures to get there? But we're not done yet. Now we have to extend a little bit further. We know what Lebesgue measure is. We know what integrals with respect to Lebesgue measure are. Now we're going to discuss the Lebesgue-Stieltjes measure, which you've seen already if you've ever taken a probability course and seen something called a cumulative distribution function. But we're going to do it in a much more generality now and have it be a very useful tool for our continued study of measure theory. But that's not all. We're also going to prove something called the monotone convergence theorem today. And the monotone convergence theorem is going to allow us to delve into the world of product measure. We're not going to finish product measure today. We're only going to touch it. And then in the next lecture, we're going to crush it and do the rest of product measure. But today, Lebesgue-Stieltjes and monotone class theorem. Let's get to the notes. And welcome back to another lecture of Statistics 571, Probability and Measure. Congratulations, we've made it to the halfway point of these video lectures. But we're not quite there yet, so we're going to have to save the cake for the end of the lecture to celebrate. It's actually birthday cake. Anyway, today what we need to do is do one more lecture about integration before we're done with this topic, and we can move on to more advanced things like LP spaces, some probability theorems, and eventually the law of large numbers and the central limit theorem. That stuff that you learned in Stats 101 class. We're going to do it again. We're going to do it better. But first, we need a lot of other stuff. Today, we're going to talk about two important things. We're going to start with a quick discussion on the Lebesgue-Stieltjes measure, and then we're going to move in to talk about product measure. Let's see if we can get through all of that because we got a lot to talk about. All right, so the first topic of today is the Lebesgue-Stieltjes measure. Stieltjes, whatever. Sorry, Tom, don't know how to pronounce your last name. Anyway, the idea of the Lebesgue-Stieltjes measure, I should maybe write that down because I'm actually doing these backwards. We'll do Lebesgue-Stieltjes first, and then we will do some product measure, and hopefully we make it all the way to Fubini's theorem before I run out of tea. Now, the idea here is that we can effectively use a measurable function to define a new measure. So this is kind of neat. The idea being that measures sneeze. I wonder how that's going to show up on the audio. Nevertheless, right, so the idea here is that if we have a measurable function between two measurable spaces, we can use that to define a new measure. And this is kind of neat because it allows us to take a simple measure, something, or maybe not simple, but something tangible, something we're used to working with, like Lebesgue measure, and then use it to define new measures like probability measures. But in general, right, the way we're going to define this is let bold X, script X, and bold Y, script Y be measurable spaces. Then we need a measurable function. Let phi, or psi, which one is that? Psi, the one that looks like a little trident, psi mapping from X into Y be measurable. In the sense of the sigma fields X and Y, right? Now, we're going to keep letting stuff be. See how many times let shows up in a math book, right? Let mu be a measure on X on, right, script x, which is the sigma field, measures are on sigma fields, then finally we get somewhere. Then we can define a new measure, which we'll call new, which is going to be mu of phi inverse. I said psi. I said it right, but I'm trying to keep with the psi notation. Psi inverse. And this is going to be a measure on y on script y, the sigma field. So what's this doing, right? What this is doing is for some, any, I guess, b in the sigma field y, nu of b, the measure, is going to be mu of phi. Why do I keep doing that, man? Psi inverse of b. So what's happening here, if we draw a picture, because I love pictures, if we have space x and maybe we have space y over here, which of course are going to look like rectangles, because why not? Then if we have some set b, what we're doing is we are mapping it back by psi inverse into some set, which is going to be psi inverse b. And then we take the mu measure of this set. So we figure out how big this is with respect to the measure mu. And then we assign that to nu b. So what this means is that really if we have a measure mu, then for any measurable function, we can define a new measure in this way. And what this allows us to do is basically take Lebesgue measure and turn it into the Lebesgue-Stieltjes measure, which is basically every cumulative distribution function that you've ever seen. And that's going to lead to a theorem. And our theorem for Lebesgue-Stieltjes measure. So first we're going to say let f, capital F, which is very specific notation, right? Because if you've ever taken a course in like basic probability or statistics, you're going to learn about CDFs, cumulative distribution functions, and we're going to use capital F for a cumulative distribution function. In this case, right, we're going to be a little bit more abstract than that, and we're not going to call it a CDF. We're going to say it's a function from R to R that is non-constant. Okay, so it's not just 0, because that would be super boring. It's right continuous. And non-decreasing. All good things. Then, given that we have this function, okay, non-constant, right continuous, non-decreasing, so it's mostly going up, or it's flat, but not flat everywhere, then what do we know? Then, basically, there exists a unique measure, which we denote by df on the reals R, such that for all A and B in R with A less than B, what we get is that the measure df of the interval A to B, which we'll do half open, half closed, because that's how we set up Lebesgue measure originally. Even though it looks kind of weird to write that, I prefer just open or closed personally, but anyway. Actually, we just learned in the last lecture you can modify anything like this on a set of measure 0. Doesn't matter, so you can change the endpoints from open to closed, measure 0, assuming, I guess, that this measure doesn't have any point masses or atoms. So, okay, we can't actually change it yet, but nevertheless, yeah, the measure df, our Lebesgue-Stieltjes measure, is going to be defined as fb minus fa. Okay, so that's pretty cool. And the claim is that it is unique. It's a measure and it's unique. So, let's prove it. Proof. So first, we're going to say let f of infinity be defined as the limit as x goes to infinity of big F of x. And similarly for f minus infinity, because we're going to need to use these values, and it's super annoying to have to write limit as x goes to infinity every time that I want to do this. So we're going to use this notation. Technically, infinity is not really a point, but we can consider the limit as this function goes to either plus or minus infinity. And yeah, we can define, and now we define an open interval I, where I is going to have one endpoint at f of minus infinity and the other endpoint at f of plus infinity. If this is a cumulative distribution function, then you get the interval 0, 1, right? Because a cumulative distribution function starts at 0, goes up to 1. In this case, it doesn't have to be a CDF. It could be any function, again, non-constant, right continuous, non-decreasing. So it doesn't have to be 0, 1. That would just be an example that's good to keep in mind because it's something that presumably you might be familiar with, and it's always nice to have some familiarity. Anyway, we need to define something else. We're going to define function g of y. Function g of y is the inf over x in the reals such that y is less than or equal to big F of x. Okay, what is that? This is kind of going to be like F inverse. F might not strictly have it's okay, right? If you have a function, I guess what, continuous increasing, monotonically increasing function, then we should be able to invert it. This one might not have the inverse may not be a proper function, but we can at least define something that's going to be like an inverse for f. Anyway, the point is we want to define df to be lambda of g inverse. I think that's what I want. Yeah. Always making sure I get the inverses right? And lambda is Lebesgue measure, of course. So we want to make sure that this actually makes sense. What I do want to do is draw a quick little picture because I think it will help with the intuition, right? Let's say we have something that looks like a cumulative distribution function. Let's say this is 0 and this can be 1 up here. So in this case, I would be something like 0, 1. And furthermore, what in the world is g here? Well, g is the smallest y. Remember, y is our vertical axis, x is our horizontal axis. So g is going to be the smallest x value such that g is going to give us the smallest x value such that y is less than f of x. So if we pick some y here on the vertical axis, then this is the smallest value, x, such that y is less than or equal to f of x. So it would be something like this. This is what I mean by it being kind of like inverse, the inverse function. This is how it's sort of showing up. G is going to take us from the y-axis to the x-axis. F goes from the x-axis to the y-axis, right? If we think about it like that. Okay, yeah, and we want to basically show that this thing makes sense. So, first, so that's basically, we want to define df this way and show it makes sense. All right, so the first thing we want to do is the first little claim in this proof is that claim is that G is left continuous and non-decreasing. Left continuous and non-decreasing. Yes. And for y in this interval I, x in R, we have that G, y, is less than or equal to x, and this is if and only if, double if with two f's, if y is less than or equal to f of x. It looks fine when I draw a picture with a continuous function, but it doesn't have to be continuous. It doesn't have to be monotonically increasing, so it could be, well, more annoying than that nice green line I drew. So that's the point, right? We want all this stuff to be true. So how do we show all this? Well, first, let's fix a y in the interval I. And let J, y, be the set of x, so it's a subset of the real line, the horizontal axis in this case. I like to think about horizontal or vertical axis just so I can remember where all these crazy sets are going to be. Anyway, this is going to be a subset of the real line such that y is less than or equal to f of x. Yeah, it's all the x such that that is less than. So in some sense, it would be like going off to the left, right? It's all the x's. No, wait, I have it backwards. We want f of x to be bigger than y, so it's like going off to the right in my little picture up there. Yeah. And we say as f is non-decreasing, if, so f is non-decreasing, so if x happens to be, this is what I kind of said out loud, if x is in J sub y, and there exists, well, not there exists, for any x prime greater than or equal to x, then x prime is also in J sub y. So this is what I mean by it kind of goes off to the right. If there's a point in it, then any point bigger than that point in value will also be in it. Okay, that was using the non-decreasing bit. As f is right continuous, right? We're using all of those nice conditions that we threw into the theorem. Don't want to waste any, because otherwise it's why include them, right? Yeah, as f is right continuous, this allows us to do sequences. If xn is in jy, and xn is a decreasing sequence to which decreases to some point x, then that means that x is also in jy. Again, right continuous would mean that we're closed on the, I guess we're closed at the left side, right? Because it's right continue of this interval would be closed on the left side because f is right continuous, which is kind of annoying, but okay, that's just what's happening here. Because it's continuous from the right, yeah. Huh. I feel like they should change the name of this, but that's okay. It's continuous from the right, right? So that's what they're getting at here, which means that the left endpoint is included, which means we can take a decreasing sequence of xn, and whatever it converges to, x is going to be in this set, as long as all the xn's are in that. Cool, so we have that type of closure. Therefore, we have that jy is going to be of the form closed bracket gy to infinity open bracket. So it's a half-closed interval. Okay, we're not quite there yet. So furthermore, if gy is less than or equal to, or not if, sorry. Furthermore, gy is less than or equal to x, and this is if and only if. I think I said that already, did I? Maybe not. Gy is less than or equal to x if and only if y is less than or equal to f of x. Remember, you can kind of stare at this picture. Again, remember that f can be more complicated than this green line I drew up here in the corner. But nevertheless, it's still a good picture to keep in mind. Now, yeah, so we have that that's true. And then also, we have that for y less than or equal to y prime, we have jy prime, make sure I get the inclusion right, is contained in jy. Right, because as y decreases, the set of everything to the right on the x-axis will increase. So as y gets smaller, the jy just gets bigger. The left endpoint keeps moving. It may not move, I guess, but it cannot get any larger. It can only get smaller. So the set will only get bigger. Great. And that means that, therefore, that means that our function g, y here, or g of y, is going to be less than or equal to g of y prime. So there's our non-decreasing that we wanted to show. So if yn increases to y, some point y, then jy is going to be the intersection of all the sets over n. I guess we could say n from 1 to infinity, of jy n. And thus, we have g yn converging to gy. And this means that we have left continuity is continuous from the left. And non-decreasing, I guess. I wrote that in the notes. That's non-decreasing, right? And this implies continuous from the left because we have an increasing sequence of y's. So I guess it's, right, if you think about that horizontal or the vertical axis, turn it on its side. As you increase, the y's are going to converge to something in that set. We're enforcing that the y's are... Yeah, I guess we're not really enforcing. I mean, the y's are just defining jy, and jy is defined in terms of f, and then, yeah, of course. So in this case, what's happening, right, is we're using this, what are we doing here? We're using jy here, jyn, as kind of like where this j set is for yn. And we're showing that for jy, this set is going to get, in some sense, smaller and smaller and smaller. We can intersect all of these. And what we're left with is this convergence, and the idea that then we know that we're going to actually converge to what we want to converge to. And that gives us our left continuity. Now comes the fun part. So next, G is Borel measurable. Why is that true? That goes back a couple lectures to the fun facts or useful facts. I thought really useful facts about measurable functions, namely that measurable function or inverse images of set functions preserve set operations. So the point is that if f, I guess, let me think. How do we want to think about this? If f is measurable or inverse images preserve set operations, and G is defined, where is G defined? Way up at the top, right? G is defined as this inf, and I know that if I have, well, actually, I guess we're kind of just done in the sense that what we're defining G as this inf over x such that the y is less than or equal to f of x. So in this case, if we take a set like these half-open intervals that we've been working with the whole time, and we know that those are going to get mapped back into a measurable set, then those are going to span, right? Those are going to generate the Borel sets, and we're kind of done, right? It's this thing is what I'm rambling about. Is the point is we have a whole bunch of half-open intervals, and if we use those, we can generate the Borel sigma field. Therefore, we have a nice Borel measure, or G is Borel measurable. Therefore, defining df to be lambda of G inverse, right? The whole point of all this nonsense up above was just to basically say that writing this makes sense. So we have G's Borel measurable. We can write this now in the Lebesgue-Stieltjes form. And this gives that if we want to measure an open, half-open interval AB like we started with, right? We kind of know what we want. We want it to be B minus A, F of B minus F of A. Well, let's see if this gets us what we want, right? This is going to be lambda, the Lebesgue measure, applied to a set. In this case, it's the set of all y such that, well, G of y has to be greater than A, and G of y has to be less than or equal to B. Right endpoints closed. Cool, so now we're taking the Lebesgue measure of this set. Well, what's that? Well, if we look at this, this is going to be the Lebesgue measure of F. Sorry, I need an interval here. Half open, FA, half closed, FB. And this is just, the Lebesgue measure is just the length of that interval, which is FB minus FA. Okay, cool, so we get what we want. Why is it unique, right? It's unique using really the exact same arguments as we did with Lebesgue measure. This idea that, right, if we define Lebesgue measure on these, let's say some sets, well, when we make this extension, we can use whatever we want. In the case of before in this course, we talked about using Dynkin pi-lambda approach to prove the uniqueness of a measure, and that's basically what happens here. The idea is that, well, this measure works basically as, so basically the ending line is that any other measure mu such that mu of AB is equal to F of B minus F of A must coincide with the newly constructed df Lebesgue-Stieltjes measure on all Borel sets, which is all we really care about, right? This gets back to the same uniqueness theorems that we proved before. All right, let's get my audio or my camera back on. This Lebesgue-Stieltjes measure stuff is going to take a while, it seems, to actually get through. Maybe I'm going to have to break this into 2 lectures, but we'll see how we do. Anyway, so now we have it. QED, we have our uniqueness here. We have the existence and the uniqueness of the Lebesgue-Stieltjes measure, and that's great because it's used for every single CDF you're ever going to look at. Yeah, that's exactly what I said in my little note here. Now we have one more fun fact about Lebesgue-Stieltjes measure, but we're going to have to define a new thing, which is called a Radon measure, because it turns out that basically, oh, that's right, this is the last little bit. There's no more theorems to prove. It turns out that these Lebesgue-Stieltjes measures are Radon measures, and it's actually kind of an if and only if thing. It's really interesting. So let me write this down. One quick definition. And this is a Radon measure, named after, I forget, Radon. I think his name was Johann Radon, but I might just be guessing that because I'm pretty sure he was Austrian, German, Austrian, and Johann is like a pretty good guess if someone's coming for that. But regardless, Radon was a mathematician, early 20th century, like most of these guys that we're talking about. Did a lot of stuff. You can read the Wikipedia page. I forgot to read it, so I don't have all that knowledge on the back of my head ready to go. Nevertheless, let omega f mu be a measure space. And, oh, not f, sorry. I want the Borel sets. Yeah. B is the Borel sigma field. Again, this is assuming that, okay, we have a topology, we have open sets, we can use that to construct the Borel sigma field. If you want, you can replace omega with R if it makes you happier. But we could define Borel sets more generally. So we'll say mu is said to be radon, if mu of the set K is finite for all compact K that are Borel sets. Right, so compact set, right? If you recall what that is, well, it depends on where we're working. Compact sets can be defined in multiple ways, depending on how abstract you want to get. If you're working in Euclidean space, closed and bounded, we're done. I think that's, I forget, Hein-Borel theorem or something. I think that's it. That compact sets are closed and bounded. Typically, we would think more generally that a compact set means that for any open cover, there exists a finite subcover of the set. And there's also some different compactness based on sequential compactness versus other types of compactness. So compactness can get kind of abstract as we move away from what we're used to being, say, n-dimensional Euclidean space. But nevertheless, in this case, we can think of it as like, okay, if I have the real line, and if I have a measure that assigns a finite value to every closed and bounded set interval, right, then we can call this radon. And I have a little note, which is most of the measures you're probably going to run into, especially if you're dealing with things like statistics, are going to be radon measures. If you're really going out there in probability theory, maybe you'll get some non-radon measures, but you're going to have to go digging a little bit further for them. At least I never encountered them in more applied statistics work. I mean, presumably, maybe someone has, but we'll see. Anyway, it's kind of neat that, so two things to note. df is a Radon measure. I mean, Lebesgue measure you can see immediately as a Radon measure, because if you have a compact set, you can cover it by an open interval on the real line, and the Lebesgue measure of that open interval is going to be bigger than or equal to the measure of the compact set, and that measure of the interval is just going to be endpoint minus endpoint, b minus a, which is finite, and we're done. And in this case, we're just transforming it, so that's good. But there's something more interesting than that. I mean, this is like, okay, well, sure, why not? More interestingly, every non-zero Radon measure on the Borel sets of the real line. Again, if we get off the real line, then compactness might not be the same, but real line, we're good. Can be written as a Lebesgue-Stieltjes measure. So that's kind of cool, I think. We'll say for some f. I mean, I think that's kind of neat, right? Because, okay, sure, of course df is Radon, but what we're saying is that actually every Radon measure on the real line, on the Borel sets on the real line, can be written as a Lebesgue-Stieltjes measure. So that's kind of neat. And I can do this in kind of one line, which is if mu is Radon on R, I guess I should say on the Borel sets of R, then define f of x to be, well, two things. It's going to be mu of the open, half-open interval 0 to x. This is if x is greater than or equal to 0, and it's going to be the half-open, oh no, I always left, it's negative, sorry, negative mu. We're always assuming well, so far we're just talking about positive measures, not signed measures. I might just try to avoid signed measures in this course. We'll see as we go forward if I get stuck in it. I did it wrong. I have to be looking what I'm doing. x0 if x is less than 0. Okay, so the claim is that if you define f to be a function like this, then it's good, right? Well, therefore, right, f of b minus f of a is just going to be mu of a b for a less than b. Cool. And therefore, mu is equal to df by uniqueness. Again, if the two measures here agree on this these intervals, then they agree everywhere on all the Borel sets by the way the uniqueness was proved. Okay, so wait, why was mu being Radon actually necessary? That's kind of an interesting question to consider, right? Well, what did Radon say? Radon said, well, it has to give me a finite value for all these compact sets. So you can think about that one. I'll leave it as like a question to consider, something you can think about in your while you lie awake at night staring at the ceiling. What would happen if, let's say, there was a compact set that had infinite measure on the real line under mu, infinite mu measure? What would that do to f, and how would that kind of break things? Things to ponder, right? All right, but man, we're already like 35, 40 minutes in, and I want to talk about product measure. So let's do that. Might have to save the final theorems for a bonus lecture, because I don't know if we're going to get through all of them, and I really wanted to eat that cake. So, all right, we talked a little bit about product measure in an earlier lecture, and now we're going to do it again, but we're going to do it more formally, because last time I was kind of just saying, okay, we have Lebesgue measure on the real line. It's really reasonable to think about Lebesgue measure, say, on the plane, where now I can take interval and interval, I can cross them and make rectangles, right? And I could extend that to higher dimensional Euclidean space. But we can more formally define the idea of a product measure on between two measure spaces. And we're going to do that by using the integral. So here's what we need. So given x and y sigma fields, as before, right? Okay. Over bold x and y, we define the product sigma field x cross y to be a v, it's unique, sigma sigma. It's the sigma field, or I guess we can call it the product sigma. Well, it is the product sigma field. We define it to be the sigma field, which is generated by the rectangles. Generated by the rectangles in, well, the rectangles of the form A times B, where A is an element of sigma field X and B is an element of sigma field Y. So this is a more general notion of rectangle, right? But it's basically saying I take something from X, I take something from Y, and I cross it. That's a rectangle. And if I take the set of all these rectangles, I can use that to generate the sigma field, the product sigma field, X cross Y. So, yeah, I wanted to make sure I'm denoting this correctly. We denote the set of all rectangles to be script R. And yeah, basically what I said above is that the sigma field generated by script R is going to be denoted as X cross Y. I guess we can put a little dot dot to say it's defined that way. Well, no. The sigma field is actually the opposite direction for the definition, right? We're defining X cross Y to be the sigma field generated by the rectangles, not the other way around. So the main goal is we want to prove some existence and uniqueness. I'm going to write down the theorem. We're not going to prove it yet because we got a lot to do first before we actually get to that proof. Yeah, maybe we can do another 2-hour lecture. Why not? Go big or turn off the video, right? Anyway, the big theorem we want to prove is existence, and uniqueness of product measure. All right, that looks kind of messily written. Sorry. Let bold X, script X, mu, and bold Y, script Y, nu, be sigma finite. Always gotta watch all these things in the theorems, right? Because it's like, be careful what shows up. Sigma finite measure spaces. we need the sigma finiteness for this extension to be unique. Otherwise, you can get some weird stuff. I'm pretty sure in one of these books, I think it was Dudley's book, that has some examples of what happens if you don't have sigma finiteness. Maybe we can look it up later. But these are going to be two sigma finite measure spaces. Now, let pi be a set function. It's going to be a measure, but it's not a measure yet. It's a set function on x cross y, such that for I guess it's not defined on all of the sigma field. It's defined specifically on x and y. What I mean by that is such that for a in x and b in y, what we have is that pi of the rectangle, right? We're going to measure the rectangle a cross b to be, well, its length times its width, right? It's going to be mu of a times nu of b, where mu would be measuring one part of the rectangle, nu would be the other side of the rectangle. Of course, this rectangle may be horrendously terrible to stare at, because it's just a general, like two sets from a sigma field rather than, say, two intervals. But nevertheless, you can think of it that way. So we have a set function, and it's doing what we want it to do on the rectangles. Then we're going to try to extend it. So given that we have this set function, then, I guess not we, pi extends uniquely to a measure on the measurable space. Oh, my laptop's not plugged in. We're going to lose power if I don't do that. Hopefully yep, I think we're still screen recording, so. Where were we? On the measurable space, which is going to be x. That's a terrible x. I need a little tighter with those double lines. X cross y, comma, script x cross script y. So it extends to a measure that is a measure, it's on this measurable space, such that for any E in the product sigma field, we define pi of E to be a double integral, and hence why I had to wait this long to do it. We need integrals. The double integral of the indicator function d mu d nu. And this will also be equal to the indicator function integrated d nu d mu. I guess, strictly speaking, in the notes I would write something like d nu of y, d mu of x, but it's kind of implied because mu is on x and nu is on y, pi is on the product space, and the point being that we can define it either way. Those two integrals are equal, and that's going to be how this measure extends. So remember, we're starting here, and we extend here, because it can be a little confusing, because we're basically going to be using pi to be what it was originally, a set function, and show that it extends to a measure, and this is how we define that measure. Okay, so how in the world do we prove that? Well, first what we're going to do is we're going to look at finite measures. So the proof outline is 1, do it for finite measures. And 2, extend to sigma finite. And as I mentioned, there are counterexamples out there. I don't remember one off the top of my head. It probably involves counting measure because it always involves counting measure. But there are counterexamples to show that you can't extend to general measures. So you can only do as well as getting... You can't get the extension won't necessarily be unique, so you run into some trouble. Okay, so what can we do? Well, we'll say fact 1, which is on R, the space of rectangles, set function... Yeah, I think I should have defined it more like that. In the notes I said on this, but the set function is really on the rectangles R. It's not really a set function on the entire product sigma field. It's a set function on the rectangles that gets extended to the product sigma field. So let's cross that out and do that. So the point is that on R, the set function pi, as defined in the theorem, is countably additive. Okay, you can try and show that yourself. It's mu, it's based on, right, pi is defined in terms of mu and nu for rectangles. Mu and nu are both countably additive. So you can kind of imagine what's going to go on here, right? If you have a bunch of finite disjoint union, well, countably, a countable disjoint union of rectangles, and then, you know, just break it up like that using those properties. So that's the first thing. I'm not going to prove that. You can try to do it yourself. It's just check the definition. Next, we can extend R, which happens to be, is it a ring? No, it's a semi-ring, I think. Yeah, it doesn't really matter. We can extend R to a field, or an algebra if you like, A, by including countable unions of rectangles. So again, R is the set of rectangles. Yeah, R is the set of rectangles. We can use countable unions to extend it to a field. The set function pi is countably additive. That's all good stuff. Now, what we're going to use is we're going to use an analog, not an analog, an alternative version, maybe not an alternative version, a different type of theorem that's very, very similar to Dynkin's pi-lambda theorem. So we're going to say we need a theorem similar in style to Dynkin pi-lambda. And this is going to be called the monotone class theorem, not to be confused with the monotone convergence theorem, which means we need a definition. Definition: monotone class. This is an alternative tool that's very similar to Dynkin's pi-lambda theorem that we can use to prove uniqueness, much in the same way we did back a couple lectures ago. So, a collection of a collection M of subsets of omega is monotone if, well, if two things. If one, for ai, I from 1 to infinity, are such that ai is in M, that's terrible script M, and the ai increase to some set A, which is the union of all of these things, then A is in M. So it's closed under increasing sequences of sets. It's also closed, well, under decreasing sequences of sets. So for AI in M, and the opposite, AI are now decreasing to A, where this would be the intersection, I from 1 to infinity, of the AI, then A is in M. So this is just two different closures. One is for increasing sequences of sets, one's for decreasing sequences of sets. And then we're going to say note a field A if, I forget the conditional, if a field A is also monotone, then it is a sigma field. Okay. I guess that makes sense, right? You can think about that. If you have a field, you have up to finite unions. The only thing you're missing is countable unions. So you would just have to check that having a field that is closed under these increasing and decreasing sequence of sets will get me countable unions. Oh yes, we're going to need one other thing. So I'll say recall. We need to redefine what a field is to make the proof that's about to come a little bit easier. So let's do that. Recall that A is a field if, well, we're going to need the empty set and we're going to need omega to be in A. And if B and A are in script A, then we defined this as B minus A is in script A. And lastly, if B and A is in script A, then the union B union A is in script A. Good stuff. But we want to replace this point number 2 with a new result, a new condition, which is that A in A implies that a complement is in A. So the claim is that I can take that middle condition and replace it with closure under complements rather than set subtraction, and that should be good. Well, this is true because if I get my set theory right, B minus A is going to be equal to B intersect a complement. So what that means is that if I include complements, that means I can do B minus A. And if I can do B minus A, then I can do A complement. So it's kind of an if and only if kind of thing, right? I just need one of these conditions. The point is that in the theorem to come, what we're going to want to do is we're going to want to use complements rather than set subtraction B minus A. It's going to make things a little bit easier. So what we're going to do in the theorem to come is we're going to remove this condition and we're going to include this condition in our definition of what it is to be a field. So that's just where we're going with this. Now, yeah, maybe we'll prove the monotone class theorem and then we will save all this other stuff for another lecture. Because, yeah, there's a lot to go through and it's probably going to take me more than an hour to prove everything. But let's do monotone class theorem so you can see what it looks like. And remember what Dynkin's pi-lambda theorem looked like. It's the monotone class theorem, not to be confused with monotone convergence, of course. And the monotone class theorem says let A be a field and M be a monotone class, such that script A, the field, is contained in the monotone class. Then the sigma field generated by A is contained, possibly equal to, possibly not, in the monotone class. So again, this is a lot like Dynkin pi-lambda. Dynkin pi-lambda says if a pi system is contained in a lambda system, then the sigma field generated by that pi system is also contained in that lambda system. So it has that same idea that as when we used Dynkin pi-lambda, we tried to set up a lambda system, or we set up a collection of sets that has a property that we want to hold. We show it's a lambda system, we show that the pi system is in the lambda system, and therefore the whole sigma field is in the lambda system. We're going to do the same thing here. We're going to have we're going to use monotone class in what's to come. Right now we have to prove that this makes sense, but you can see in a way how we're going to use this again. Now, which way does it go? I believe monotone, so in this case, the condition, the input, is stronger than Dynkin pi-lambda. We have to start with a field, not just a pi system. A pi system only has one condition. I'm closed under intersections. Field has a lot of rules. But monotone classes are more general than lambda systems. Lambda systems have more rules than monotone classes. So in some sense, it's kind of like we have to pick an input and we got to get an output. Do we want a simple input like a pi system and a more complex output like a lambda system? Or do we want a complex input like a field and a simpler output like a monotone class? Some of these can be useful in some contexts and others can be useful in others. So it's good to know about both of them. And we're specifically going to use this again to prove this great theorem up here about the existence and uniqueness of product probabilities, product measure. Not necessarily probabilities, just product measures. But we have to prove that this theorem actually makes sense. Or is true, I guess. So, first we're going to define little m of A to be the minimal monotone class such that sigma, oh no, such that, sorry, not sigma, such that A is contained. Oh, let's say the minimal monotone class, let's try to write a better sentence here. The minimal monotone class that contains A. Now the goal of this proof is to show that sigma A, the smallest sigma field containing A, is contained in M A, the smallest monotone class containing A. We can think of the smallest monotone class containing A as the intersection of all monotone classes that contain A. That's one way to think about that there is sort of a minimal monotone class. If we think about it going upward, right, we can start with a field and we can consider the closure under these monotone sequences of sets. So that's the goal. The method that we're going to do is to show that little m, A, is also a field. And thus a sigma field. And thus contains sigma A. Now remember, sigma A is the smallest sigma field that contains A. We're just showing that this minimal monotone class is a sigma field. It may not be the smallest sigma field, but if it's a sigma field, if it contains A, it has to contain all of sigma A by the minimality of sigma A. All right, so we're going to do this in, I guess, 2 steps. Step 1. And that's show. I guess it's basically, we're going to be doing exactly what we're doing up here. Step 1 is, I guess we need to do complements and we need to do finite unions, right? Because we want to show that this thing is a field. So we want to show that M A is closed under complements. If we really wanted to, we could try to argue that it's closed under set subtraction, but I think complements is just easier, so that's why we're doing it this way, and that's why I was ranting earlier about why we can replace set subtraction with complements in the definition of a field. Again, different textbooks use different definitions as well, but they're all like equivalent objects. Anyway, let F, again, we're going to use this same kind of trick where we're going to say F is some set of sets. It's a collection of sets. It's all the A that live in our monotone class such that a complement is also in our monotone class. So the goal is to show that F is all of the of MA, right? That all, for any set A in MA, its complement is also in it. But we have to show that. So we're just going to say these are the sets where we can take complements and it's closed under complements. So therefore, script A is in F, not in F, sorry, a subset of F, since, well, A is a field. It's closed under complements. So, of course, A is going to be in there. What else is in there? Well, next, we'll say for a sequence of sets I from 1 to infinity, such that these AIs are in F. It's always good to know that there's something in F that we can take a complement of. We know we at least have the entire field. script A. So if I have a collection of sets AI that are in there, and these AIs increase to some set A, defined again as the union of those, then AI complement is also in F, right? Because we know we can take complements of the AIs. The question is, okay, yeah, making sure I wasn't doing this backwards, right? Okay, we have that AI complement is in F, and furthermore, we have that AI complement is going to be decreasing, right? If the AIs are increasing to A, the AI complements are decreasing to A complement. And this is equal to an infinite intersection. I don't need to put a parenthesis there. I from 1 to infinity of AIC, and this is going to be the complement of the infinite union, or the complement I from 1 to infinity of the AIs all complemented. Right? If I take a whole bunch of sets, I union them together, and then I take everything that's not in that union, it's the same as taking each piece individual and intersecting it, because the intersection of the AI complements means I have to not... How do we want to think about this? AI complement means I'm not in AI. The intersection means I have to be in all of the complements, which means I can't be in any AI. And then the union is all the points that are in at least one AI, and the complement of that would be a point that is not in any of the AIs. So you can kind of like talk it out to make sure that kind of makes sense. Okay, what does this all mean? Well, therefore, we know that the union, I from 1 to infinity, of the AI, which is equal to set A, is going to be in F, because I just showed that its complement exists, right? Its complement, that is, the complement of this union, is in MA. So what does that mean? Therefore, F is monotone, and F is contained, or possibly equal to, it's going to be equal to, but possibly equal to little m of A. So what we're saying is F is monotone. F is at least contained in A, MA, because we know it's closed in that way. But now we can do the same for AI decreasing to A to get that F is in fact equal to MA by minimality. I guess it's half monotone. I should say monotone in an increasing, and then we can do it the other way to show that it's monotone in the decreasing sense. I think I need to reword this to make it slightly clearer, but yeah, by minimality of MA. Therefore, MA is closed under complements. All right, what's the logic here? The logic, because I think it got a little bit muddled there at the end. The point is that I want to show that F, which is the sets that I'm allowed to have, that I have complements of in M, A, is monotone. So what we do is we start with A. First of all, F contains A. Okay. F contains script A. And we can show that if F contains a union, and basically an increasing collection of sets, then it's going to contain its union because both its union and the complement of its union exist in MA. And similarly, when we go down with an intersection. So what this means is that F is monotone, F contains A, F is within MA, but MA is minimal monotone that contains A, therefore F and MA have to be the exact same thing. Whew. It always sounds kind of crazy when I say this out loud. I can imagine just taking the audio of this without any actual context. Anyway, the point is that because F is equal to MA, F is all the sets that have complementation. That means that every set in MA has its complement also in MA. So that's good. Step 2, show that MA is closed under finite unions. Okay, so how are we going to do that? We're going to define another collection of sets. We define a new collection, which is going to be, how do I do a script G? Script G, I guess, looks like that. Script G1. This proof is going to look very similar to one we did before, where we kind of stepped up. I'm forgetting exactly which one it was. I'd have to go look it up, but we did do a proof very much like this in an earlier lecture. We're going to start with G1. I think it was in Carathéodory's extension theorem, part of that, but I can't quite remember right now. It was either that or the uniqueness in Dynkin's pi-lambda theorem. Anyway, G1 is going to be the set of A in MA in the minimal monotone class, such that A union B is also going to be in MA. And this is for all B in script A, the field. So basically what we're saying is G1 are all the elements in the monotone class that I can union with an element of the field, the generating field that generates the monotone class, and the union of those two things will be in the monotone class. So we'll say as with F from above, we note that A is contained in script G1, not an element of. I keep doing that. It's a subset of. And this is, again, A is a field. So, of course, you can take unions of elements, finite unions within a field, still a field. And second, so this is A is in there. And it turns out that G1 is monotone. Don't believe me? Well, let's try to show it. Let's get rid of that period. G1 is monotone as the union I from 1 to infinity of AI unioned with some set B is going to be the union I from 1 to infinity of AI union B. And this is going to be A in the monotone class. And similarly, if we have the intersection I from 1 to infinity of AIs, right? I'm kind of jumping ahead, but it's the same AIs as above. If we have AIs increasing to the union, then we can union that with a B and show that the union I from 1 to infinity of AI union BI is equal to that, so therefore it's also in the monotone class. Now with the intersection, we're going to do the same thing. We take the infinite intersection, we want to show that we can union it and still be in the monotone class with an element B. So what we do is we union it with B. Then we just have to, well, I guess not actually work that much harder. We just note that this is the infinite intersection of AI union B in the parentheses. And since this is, because M is a monotone class, we know that this thing is also in MA. So simply what we're saying here is that it contains the union of the AIs, or G1 contains the union of the AIs. It contains the intersection of the AIs if the AIs are increasing or if they're decreasing. Therefore, G is monotone. Therefore, by minimality, our G1 is monotone, and hence, as before, G1 is equal to MA. Right? It has to be contained within MA, but MA is also minimal monotone, so it has to be the entire thing. Again, this argument is really based around the minimality of MA. So what does this mean? We're not done yet, and that's hence why I keep writing G1. Therefore, MA is closed under unions with the field A. But we don't want it to be closed just under taking unions with elements of the field A. We want it to be closed under any union, any finite union. So we're going to do that by kind of, I guess, bootstrapping our way up. And we're going to define G2. More banging upstairs. G2 is going to be B, all the B in MA, such that A union B is in MA, not A, but script A. And this is for all A in MA. Okay, so this is the one we want to show is monotone and the same as MA, because then we know we can take unions under any element of MA. So this isn't so bad, right? First of all, we have, once again, that script A is contained within G2 here, as we did before, right? This is since B, since if a set B is in A, then A union B is going to be in MA. And this is for any A in MA. Right? This is coming from, from the argument with G1. So again, what we're saying here is that for any B in the field A, we know that the union of A and B is going to be in MA. That comes from G1 up above. This thing here in blue is, where is it? This thing up here. So that's why we need G1. We can't just attack it directly with G2, is we use G1 to show that we can take unions with elements of one element in MA and one element in A. And then what that implies here is that the field A is also a subset of G2. That's good because, again, we want to use the minimal monotone property. And then we'll say, Based on basically the same argument as before, G2 is also monotone. I'm not going to redo that because, yeah, we kind of already did that, but it is monotone. All right, so in some sense, we're kind of done because hence G2 is going to be monotone. It's contained in MA. MA is minimal monotone. Therefore, they're the same thing. And then, yeah, we're done. Because, therefore, MA closed under finite unions. Good stuff. Therefore, it's a field. Therefore, MA is a field. And by my claim above, also a sigma field. And thus it has to contain sigma A because sigma A is the minimal sigma field that contains A. So it has to be, that sigma field has to be contained in any other sigma field that contains A. All right, we're done. Yeah, I think that's probably good for today because I'm kind of tired and we still have a lot to do to prove that existence and uniqueness theorem for product measure. What we're going to do next is we're going to prove a lemma, and this lemma is going to be specifically for finite measure spaces, and it's going to allow us, in some sense, to define that this extension makes sense for finite measures. Then we're going to hit the actual proof of the theorem and show how we can extend this. And then we have one other bonus theorem before we're done with product measures, the famous Fubini's theorem or the Fubini-Tonelli theorem, which allows us to swap the order of integration, something that you've probably been doing since calculus class, but now we're going to do it in a proper measure theoretic sense. So stay tuned for that lecture. It'll be coming soon. And I think I'm going to eat some of this cake. See you next time.